For the second part of the Chapter 5 lecture, we're going to look at type 2 metal compounds, and we're going to look at molecules. Okay, so type 2 metal cations. Type 2 metal cations are ones that can form one or more type of cation. So they can form at least 2, sometimes even more than that, 3 or 4 different types. So where in the periodic table are most of the type 2 cations found? So remember from the last lesson when we did this, the most of our type 2s are found right here. They're going to be in our transition metal area. So they are mostly transition metals. Mostly transition metals. So where else can we find them? So these ones down here, a lot of these are also type 2, so they can also be intertransition. We don't see those a whole lot. So also intertransition, and also in here a little bit. So for most part, group 4A metals and 5A metals, we'll see this sort of block in here. So 4A and 5A metals. 4A and 5A metals as well. And so most of the time, again, we're going to be seeing transition metals for this. And again, 4A and 5A, these metals are pretty common too. These include things like tin and lead and bismuth and stuff like that. Okay, so let's look at how our rules change when we have a type 2 compound. So since they can form more than one type of charge, we're going to use all of the rules discussed before. So all the rules are the same for type 1 compounds with just the addition of one rule, and that is that we're going to include the charge of the metal in Roman numeral in parentheses when we name the metal. So it's really only going to change how the compound is named. The formula, it's not going to change at all how the formula is written. Okay, so it's best seen with a couple examples here. Before we get to these examples, I want to kind of do one real quick one. So for example, iron. Iron falls in the transition metal category. Iron can form Fe2+, quite common, and Fe3+, a little more common. So we have 2 different types of iron. So this one would be called iron 2, and this one would be called iron 3, where we put the charge in parentheses using Roman numerals. So our Roman numerals are 1, 2, 3. When we get to 4, it's 4 with an I, then a V. 5 is V, and then 6 is VI. 7 would be VII. Don't know that it goes much past 7. Okay, so this is what we mean by Roman numerals 1, 2, 3, 4, 5, 6, and 7. Okay, so write the formulas for copper 2 iodide and tin 4 carbonate. Okay, so this is kind of nice. Before, when we had to do this, we had to go look our metal up on the periodic table, and we had to see where it was located and determine the charge from there. Here it's given to us. So we have Cu2+. And again, we know that it's +2 because of that there. And then we need to figure out what iodide is. So we grab our periodic table. Iodine is here. So it's going to form a -1 charge. So we have Cu2+, and we have I-. So using our rules for formulas from before, we would get Cu I2. So we would need 2 of these to balance the charge of that. Okay, next we have tin 4 carbonate. So tin 4. So tin is Sn. So Sn 4+. Carbonate, if we grab our list of polyatomic ions, so carbonate is here. That is the CO3 2 minus. So here, let's zoom in on that. So carbonate is our CO3 2 minus. Okay. CO3 2 minus. Okay, so finding our formula here, we have tin has a +4 charge, carbonate has a -2. To make these two neutral, I would just need to add another carbonate, so 2 minus 2's would cancel that +4. So we get SnCO3 2, where again, since this is a polyatomic ion, we make sure we put it in parentheses and then put our subscript after that. But again, we treated it just like we did iodine. The only difference is it's a group of atoms that came together to make that charge instead of just one. So making the compounds exactly the same. We're just looking to balance the charges to make those compounds neutral by looking at the charges of the anion and the cation. Naming them from a formula is a little bit more difficult to do. We have to figure out what the particular variety of nickel, or in this case molybdenum, is for this compound. So we'll start here. We have NiNO3 3. Okay, so we're going to use two things to help us do this. One, we know that this compound is neutral. So whatever this is and whatever these are, this whole entire thing has to be neutral. And second, we always know the charge of the anion. There weren't any type 2 anions. It was all cations that had charges that could change. But all of our anions always have the same charge. So we're going to look up our nitrate. We're going to pull our chart out here. So nitrate is NO3 minus. So NO3 minus. So if I look where my negative is over here, each one of those nitrates is a -1. So I have 3 times -1 equals -3. So all three of those nitrates together tell me I have a -3 charge. For this compound to be neutral, that nickel has to be +3. So the name of this is nickel, NiCkel, and then I put the 3 to tell it's the nickel 3 variety, and then I name my anion afterwards, which is nitrate. So we have nickel 3 nitrate. Okay, so we're going to do the same thing for MoN2. So we have MoN2. Okay, so I know that my negative and my positive have to balance or cancel each other out. So I'm just going to look up what I have. Okay, so we have 2 nitrogens. So if I look at my periodic table, nitrogen is right here. So nitrogen as an anion forms a charge of -3. So we have 2 nitrogens with a -3 charge. So 2 times 3, so this is total of -6. So we have -6 over here. So in order to balance that, molybdenum has to be +6. So we have molybdenum 6, and then we have nitride. So because it's the element version of this, again, so instead of nitrogen, we're going to change the ending of the anion to "ide", so molybdenum 6 nitride, where again, we had to figure this out based off of the charges here. Okay, so we'll do some more practice with this in the practice videos for this chapter. It does take a little bit of practice to do. Okay, so next we're going to look at naming what are called binary molecules. So binary molecules are formed from 2 nonmetals. Any molecule with more than 2 different nonmetals has a more complex naming system that will not be discussed in this course. So we're just looking at molecules that have, say, nitrogen and oxygen, or carbon and oxygen, or silicon and sulfur, things like that. So just 2 different nonmetals. So name 10 elements that form molecules. Okay, so we're looking at our nonmetals. So kind of this zigzag line right here is separating our metals from nonmetals. So we're looking at all of these ones that formed anions. Those are all different things that can form molecules as well. So the big ones we're going to see are hydrogen, and we're going to see a lot of carbon, nitrogen, oxygen, chlorine, bromine, sulfur, phosphorus, and iodine. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm missing one. And we'll go selenium. So these are the ones we're going to see forming our molecules. Okay, where again, these first handful of ones here, you're going to see much more than, say, some of these ones down here. Also, when we start looking at molecules, some of our larger noble gases will form some molecules too. So you might see a little bit of xenon, krypton, and sometimes argon in there as well. So rules for naming. The nonmetal furthest to the left, excluding hydrogen, is named first with a prefix indicating the number of atoms present. So we're going to take the subscript of our molecule and turn it into a prefix. So this is the only type where we're actually going to use numbers to indicate the subscript. Okay, so this type here, we're actually going to say how many of each type of thing we're going to form. Where above, we didn't do that at all. We essentially, if we had numbers, that was just indicating our charge, and the ones we talked about earlier didn't indicate how many of anything we had at all. But this type, we are going to use numbers to indicate how many we have. So the other nonmetal is named seconds with its suffix ending in "ide," with the suffix "ide, and again, using a prefix to indicate the number of atoms present. When writing the formula, the prefix determines the subscript. So our prefix will determine our subscripts, and when going the other way, the subscripts indicates the prefix needed. So here's a list of prefixes. We have 1 is called mono, 2 is di, 3 is tri, 4 is tetra, 5 is penta, we have hexa, hepta, octa, nona, and deca. So whatever our prefix is, that's going to be the subscript we're going to have, and vice versa. Whatever, if this is our subscript, that's going to tell us what prefix we need to use. So for example, why we do this, before I kind of get to the examples here, why we do this is because we can have different combinations of nonmetals to form molecules. And one you would probably be familiar with are molecules of carbon and oxygen. So you probably know that we can form CO2 with carbon and oxygen, but we can also form CO with carbon and oxygen. So it's not like our metals and nonmetals where they came together and they had to form a particular combination based off of their positive and minus charge. So we're hooking together things with springs. So it all depends on how many springs you can form as to how many different varieties of things you can make. So this one here, CO2, and then we have CO. So mono is 1. When it's the first one, we don't indicate that, so we know this is carbon. And the prefix 2 is di, so we have dioxide. Same thing here, when mono is the first one, we don't include that. We have carbon, and since we just have 1, we have monoxide. Okay, 2 different compounds with 2 very, very different properties. This one with 2 oxygens, this one with 1. So we do indicate that in the name. Okay, so again, that is important to realize with these, and we'll see this in chapter 10, how the bonding, how things form with covalent bonds is much, much different. With ionic compounds, we were just making them neutral based off of charges. These ones here don't have charges, so we can form many, many different types of combinations of things. Okay, let's look at our examples. Write the formula for sulfur dioxide and then dinitrogen pentoxide. Okay, so sulfur dioxide. So when there's not a prefix here, that tells us we have 1. And if we look at our di from the chart tells us that this is 2. So our sulfur has a subscript of 1, our oxygen has a subscript of 2. So we end up with SO2. Okay, so we look at our next one, we have dinitrogen. Again, our di tells us our suffix, or excuse me, our subscript is 2. Then we have pent. So pent is 5. So we have 5. So we have nitrogen with a subscript of 2 and oxygen with a subscript of 5. So we get N2O and 5. Okay, so another maybe thing you've seen here, when with oxygen, we drop the A or the O in the prefix name. So we ended up with pentoxide instead of pentaoxide. That's just sort of a naming thing that we do. And it's really just with oxygen we do that. Someone along the line decided that saying 2 different, vowel combinations at once maybe wasn't the best thing to do. Okay, so name the following. We have XeF4. So xenon is the first, and it is mono, so we don't include that. So we're just going to write xenon. So our fluorine is going to become fluoride because it's second. And then 4 is going to be our tetra. So xenon, tetra, fluoride. I turned fluorine into fluoride, and then since that subscript was 4, my prefix tetra was used. So next we have Br2Cl6. So 2 bromines, it's first, so we're going to name it first. So 2 is di. So we have dibromine. And then our 6, we look up here, is hexa. So we're going to have hexa. And then chlorine is going to become chloride. Okay, so these ones are really nice because if you have this chart handy, all you have to do is turn that subscript into the prefix in the name or vice versa. Figure out what that prefix in the name means, and then that just becomes your subscript when you make your molecule. So out of all of the ones we're going to discuss in this chapter, this one's probably the most straightforward and sort of easiest to recognize.